So we're looking at horizontal motion. So the question reads, a particle P is moving on the x-axis with a constant deceleration of 2.5 meters per second squared. I always tend to draw a diagram, and I would advise you do the same. So the particle is moving horizontally. Here's my starting point, and then there's my finishing point. It starts at time t equals to 0, so I'll indicate that it starts at time t equals to 0. And at time t equals to 0, the particle passes through the origin, so I'll label this as O, moving in the positive direction of x with a speed of 15 meters per second. So at this point here, it has a speed of 15 meters per second, which I'll indicate here, 15 meters per second at this point here. And then it goes on to say, find the time between the instants when the particle first passes through O and the instant when it returns to O. Now this is interesting because since the object is decelerating, as it's mentioned here, so I'll indicate the deceleration, double arrow, and I'll indicate deceleration with negative 2.5 meters per second squared. So you either show the double arrow going to the right with negative 2.5 meters squared, or you could show the acceleration as 2.5 meters per second squared to the left. It's either one or the other. Okay, so don't get them mixed up. You wouldn't do both negative and change the direction. I prefer to keep it to the right and indicate deceleration using negative. So since it's decelerating, the object will go to a point where it's slowing down from the 15 meters per second until it becomes 0, and then it will then start returning back towards the origin again. So the object moves like that, and then it starts coming back. At this point here, I'll indicate this point here as being, let's say, point A. And at that point, where the object turns or changes direction, it's very important to understand what's happening here. So anytime an object changes direction, it will be momentarily at rest, instantaneously at rest. So the velocity will be 0 at that point. When an object changes direction, it is instantaneously at rest. Velocity equals 0 at that point. Now, since this object has only acceleration of minus 2.5 meters per second squared acting on its return journey, when it comes back to this point O, so I'll label this as O1, and then when it comes back to the origin for the second time, i.e. O2, it will have the same velocity as it had originally at t equals to 0, which was 15 meters per second, but it will now be in the opposite direction at O2. It will be acting that way. Okay. I'll indicate my acceleration is already indicated. It's minus 2.5 meters per second squared. For the entire journey, I'm going to take right as positive, as you can see here, which I've indicated. I'm taking right as positive. So let's go and take a look at how we would solve part A. So to find the time between the instants when P passes through O and the instant when it returns to O again, we'll use Suvat. So I'm going to say I'm going to go from O1. I always define the start and finish point. I'm going to do Suvat between O1 going to O2, and I'm going to take right as positive for my journey here. And always lay out the problem by writing down then SUVAT, Suvat, and what these things are. So what is S? Well, what is the displacement from O1 to O2? The displacement is gone a certain distance, come back. The displacement is how far it is from the starting point. It's 0. What is the initial velocity at 01? It's 15 meters per second. What is the final velocity? It's minus 15 since we're taking right as positive. What is the acceleration? It's minus 2.5 meters per second squared since we are taking right as positive. And we were asked to find out what the time is. So I need an equation involving time and 3 of the other variables. All of our Suvat equation involves 4 of these variables. So we can use quite a few. I'm going to go and find a Suvat equation that gives me, well, I'll go and use S. I can use S, I can use U, V, T. There's quite a few I can use. So let's decide on one. Suppose I want to use V equals U plus AT. So V is equal to U plus AT. So V is known, U is known, A is known, and T is the unknown. So that's fine because I have one unknown here. So using this, I'll go and substitute the values in V. U is minus 15. Oh, sorry. Wait. V is minus 15. U is equal to 15 plus acceleration, which is minus 2.5. And T is the unknown. If we then go and rearrange and solve this here, so we have then minus 15, minus 15, all over minus 2.5, that will give us what T is. And that gives us 12 seconds. So here we've found out the time it takes for it to go from O and then return back to O. And then it asks us to find the total distance traveled by P during this time. Now, in order to find the distance, we need to actually break this journey down into O1 to A, because if we just look at O1 to O2, the displacement is 0. Now remember, displacement and distance are not the same thing when the object changes direction, but displacement and distance will be the same thing for the duration of the journey where the object hasn't changed direction. So if you look at starting from O, as we travel right here, the displacement and distance are the same thing. It's still the same thing. Displacement and distance are the same thing until this point when the object starts changing direction. From this point onwards, now the displacement and distance are 2 different things. So now we're going backwards. The distance covered is all of the highlighted part, so it's the yellow plus the green, whereas the displacement up at this point is only from O1 to there. That would be the displacement. So it's very important to understand the difference between displacement and distance. Now, as we keep on going back, the distance that we had going from O1 to A is essentially doubled going back here. So if we want to find the distance, what we would do is we would work out what the distance is before it changes direction. So all the way from O1 to A. So let's focus on that, and we'll then work out what that distance is. So I'm going to, for part B, start by writing down again where I'm going to do Suvat or apply Suvat between. I'm applying Suvat between O1 and A. I'm going right as positive. And then I'm going to start by writing my Suvat again. S-U-V-A-T. This time I'm trying to work out what this displacement is from O1 to A. The initial velocity at O1 is the same as before, 15. The final velocity, which is now at A, since that's where we're going to, we know is 0 because that's where it changes direction. The acceleration we know is minus 2.5. So I have three quantities here. That's enough to find out the displacement. I could work out the time as well. Now, since I worked out the time in part 1 to be 12, all the way from O1 to O2, we know that O1 to A then must be half, because we have constant acceleration throughout the whole journey here. But I'll go and use these quantities here that I've got V, U, A, and S to form an equation. So the equation that I can use here is V squared is equal to U squared plus 2AS. Substituting in the quantities that I have, got 0 squared is equal to 15 squared plus 2 lots of minus 2.5 times S, which is what I'm trying to work out, which then gives me minus 15 squared over minus 5 is equal to S. So S in this case is equal to 15 squared, which is divided by 5. That gives us 45 meters. Now this note here is the distance from O1 to A, i.e. the highlighted bit here. Now we are asked for the total distance travelled by P on its journey all the way from O1 back to the origin again. So the distance will be double that. So total distance is equal to 90 meters, double of the 45 meters. That's my answer.